Okay, so let's look at model 1. So for model 1, we're going to be looking at Q8 elements, 2x4 pool. 1 is the name of the file, so we're going to be pulling on this element here. And so let's look then and interpret what we see. Okay. So there's a couple of things that we're going to be looking at. We're going to say, let's run the file. Let's determine if the structure is in equilibrium for all simulations. So what we want to look at is force equilibrium and XY moment equilibrium for the discrete structure. So determine if the structure is in equilibrium. So I'm going to type here maybe in nodal equilibrium. So this is for the discrete. Nodal equilibrium is clear. So we'll be looking at sum of forces with each of these nodes. That's what we're going to be looking at. Okay. So here's the program what we're going to do is just launch from, here's the input file magnification factor. So we can see what's going on. We're going to be looking at reaction forces. So we're going to print all the individual applied reaction forces that we have. So we can open up the input file, Q8 2x4 pool 1, Q8 2x4 pool 1. And so to understand what the reaction vectors can look like is we need to understand the prescribed displacements so that we understand. So essentially the first reaction force is going to be something in the x direction. This is going to be reaction forces in the x direction, and here it's going to be around reaction force in the y direction, which we should be 0. Okay, there's no loading applied in the y direction, so the reaction in the y should be 0. We can immediately see with a sanity check whether things are working or not. Okay, and then we can look at the sum of the forces along x and see that it indeed the reactions indeed cancel the 600 that's been applied. Let's see. So it's magic. Let's run this file. So first off, what we see is when we run it, there's the distribute load. Actually, the deformed structure, undeformed structure, Poisson's contraction. So this is the same as what we saw yesterday when we were looking at yesterday's file. Okay, but let's look further now. I think the difference is yesterday's one we applied 100 Newton load, and here we applied 600. Okay. Von Mises, if you look at what's going on with von Mises, lots of large stresses here. If you look locally, far away, stress is essentially going down into a ballpark of about 150. Thereabouts, can we see that? And so what's important to understand is if we were interested in the answer close by to where we applied the load, then we would be making a big mistake now, because we would be looking at stresses in this range, all locally localized effects because of that point load that we're applying here. So if I were interested in the answer close by to where we applied the loading, I would have had to make the effort of saying, let's model this properly. We can't just model it as a point load. Okay, so this is step 1 to understand. Step 2 to understand is if I were interested in the answer far away from where we applied the load, like here for instance, then I could easily say, wow, fantastic, I would be fairly accurate in the answer, even though we made an approximation. We simplified the way we modeled the distributed load on this right-hand edge. The answer here is still, it's essentially spot on, what you would see. So let's go down and make sure that it's spot on. So if I look at this sigma xx, if I look across here, I'm in this color here, around about the 150 domain. Beautiful. So here the answer is very accurate. Anywhere here where, look at the variation that we would see in stress. If I were to be anywhere here, I would go from something like minus 248 sigma xx up to 550 by just looking at the stress variation along this edge. Okay, so that's important to understand, is that this would be very inaccurate. Close by, where the load is applied, if I'm interested in the answer there, big problems. If I'm only interested in the answer far away from where I applied the load, I'd be very accurate with the answer, and I got away with modeling a distributed load at this edge in a simplified fashion. Okay, so let's look at equilibrium, sum of forces in the x direction. Sorry, let me just show you sigma yy. That's what we see here. If I look at, there's a large variation of sigma yy here. Far away, we see no sigma yy. And same for the shear. If I look close by to the shear, variation here is of course quite a lot. If I look far away from what the shear is, essentially then it's close to zero, as what one would expect to see. Okay, so let's look at the sum of, let's look at the reaction forces. So the individual reaction forces are, remember the second one was supposed to be this, in the y direction should be zero, and indeed it's zero. The reaction force in the y direction is zero. Okay. Another important thing I want to show you is by applying a point load here and looking at the reaction forces here, you can see the reaction forces result in a nice distribution of load forces here, yeah, stress there, nice distribution of stress here, nice distribution of stress here. So essentially the reaction forces are going to follow, they will follow the consistent nodal loads reaction forces. That will recover that from them, and I want to show you what they are. So the reaction forces, if we go essentially from these nodes, so let me show you here. So let's go down there. It's here that I want to show you. If I show you the reaction forces going from here to here to here to here to here, I want to show you what they are, and they are essentially minus 50. Okay. Not 100% minus 50, but it's close to minus 50.12. So that is that. Okay. Minus 200. Minus 100 for the mid-side one. So minus 100 for this one. Minus 200 for the top middle one. Minus 200 and minus 50 in there. And that's beautiful, because if I have a 300 Newton uniformly distributed load across this element, I'm going to remind you again, 1/6 of that, the same split as what we saw for essentially distributed body force in 1D is now the same as what the load, how it will distribute as a traction in the 2D case. So the body force distribution in 1D, the same ratio you'll see for the distribution of the traction, surface tractions in 2D. So from 300, 1/6 is 50, 2/3 200, a 50 from this element, a 50 from this element, make it minus 100, minus 200, 200, and then essentially another 50 for those 1/6 and 2/3 distributions. So here what we see is it's actually a way for us to we can even use this as a way to recover what is the distributed loading when we want to follow a consistent nodal loading. Okay, so now we can go and say all the sum of forces in the x direction. Take this, take this, take this, take this, take this, and let's sum it all together. So that's minus 50, minus 100, minus 300, minus 500, minus 600. And you can see there, essentially we get minus 600. Beautifully, up to machine precision, equilibrium is satisfied. Okay, so that's that, what we see there. Sum of forces in the y direction, 0 and 0. No, 0 applied and 0 reaction. And then I say, we can't skip this. We have to look at what is the sum of forces in the sum of moments. And so we can say, let's take sum of moments around any point, and when we go through that and calculate it, we see that it's 0. Like we discussed already, 150 MPa stress that we expect to see. And now if you look at just quantifying what you saw now visually, I've just written it down here for you so one can look at that. Stress close to where we applied the load is I think it was 550 MPa for SXX for the stress in X direction, 200 MPa for the shear, and between 0 and 101 for the shear, and around 200 for Y direction stress in the sigma y1. Okay, and then shear between 0 and 121. And we know the answer should have been just sigma xx, 150, 0 for shear, and 0 for stress in the y direction. Okay, sigma y1. So that's important to understand. So hopefully this is now first illustration where things are nice and clear. Look at that, that's key to see. Okay.